Welcome to this session. So in this session we are going to discuss about waveguides. What are waveguides? Prior to that we discussed about transmission lines. It's clearly the transmission lines will be useful for transmission of electromagnetic wave at very low frequencies, medium frequencies up to high frequencies. But greater than 3 GHz frequency, it is not possible to transmit the signal through our transmission line. So what we do is we will go for another type of physical medium, that's a guided medium called as waveguide. Waveguide is simply remember that waveguide is a hollow metallic tube. In most of the cases it is hollow, sometimes it will be filled with some dielectric medium. So a metallic tube which is of any shape, that may be of rectangular tube or a circular tube or a square tube or which may be some clipped, right, whatever it may be. So it is some metallic tube which will be useful for transmission of electromagnetic wave through a successive reflections. The electromagnetic wave will be successively reflected within the boundary, it's inner walls of our transmission line. It's called as waveguide. That's through that particular technique the entire electromagnetic wave will be transmitted from source to load. So here clearly we are supposed to observe what are different shapes we have. Different shapes of our waveguides, like a rectangular waveguide. Simply this is a rectangular waveguide, that what I am drawing is a rectangular waveguide. You can imagine a rectangular tube. So this is the rectangular tube that what we have simply called as a rectangular waveguide, and so we have two dimensions for this one, the breadth represented with A and its a width represented with B. Here we are supposed to consider only the inner dimensions of our rectangular waveguide, not the outer dimensions. The inner walls only describes how the wave is propagating, through them only the reflection will take in place. So what they do is the inner walls will be preferably coated with either gold or silver to avoid the losses or to reduce the attenuation factor. And similarly we have one more type of waveguide, that is circular waveguide. The name itself indicating that the shape of the waveguide is like a circle. So this is a circular waveguide. Here we are supposed to consider the radius of that waveguide, the inner radius of the waveguide as A, that will play important role while the wave is propagating through it. Similarly we have one more type of waveguide. So this is another type of or another shape of waveguide that what we have, that was clipped. This is for some special applications. Or some elliptical type of waveguide will be there. Instead of circular tube we need to consider an elliptical tube. Or sometimes we may have a rectangular is already over, this is a square type of waveguide will be there. So if you observe all these waveguides, all they have a similar phenomena, that all they are made up of a metallic walls, that it contains 4 metallic walls. This will contain a single metallic wall, this also contains a single metallic wall, this is more number of walls will be there, and in between them some dielectric medium will be there. In most of the cases only air will be there, that's a simple hollow tube will be there, and all these inner walls will be coated with either gold or silver to reduce the attenuation and to get more efficiency. Like this different types of waveguides will be there. All these waveguides will be useful for transmission of electromagnetic wave at very high frequencies and microwave frequencies only. Clearly remember that point. Transmission line has no such phenomena, but at high frequencies if you are transmitting the signal, attenuation will be there, and our waveguides will not provide attenuation that much at high frequencies, that is greater than 3 GHz frequency. All these waveguides will be useful for transmission of our signal. So what we do is, just in brief we will observe what are different similarities and dissimilarities between transmission lines and waveguides. So just observe the similarities between transmission lines and waveguides. Here I will consider a transmission line. All these are just very much known to us, and these are waveguides. That WG shortly stands for waveguide, right. Now in the transmission line we observed some attenuation while the wave is traveling through the transmission line, that is alpha will exist for that particular transmission line. Similarly for waveguide also the attenuation factor will comes into the picture. So we are supposed to remember that alpha will exist for waveguide also. Clearly this is one similarity between these two. And when we are connecting load, some reflection will be there. That's why we are calculating the voltage reflection coefficient for transmission line. Some reflection will be there from the load if there is some mismatching. Similarly here also reflection will be there for a waveguide when there is some mismatching. At load if you have any mismatching, definitely some reflection will be there. Whenever there is reflection, definitely standing wave ratio comes into the picture. Here also the standing wave ratio comes into the picture. Like this, just these three are three similarities between our transmission lines and waveguides. Now, what are the dissimilarities between transmission lines and waveguides? They are very simple. As I said, our waveguides are useful for transmitting very high frequencies and microwave frequencies only. Clearly, there is a cutoff frequency for that one. That beyond that particular frequency only, it will useful for transmission of the frequencies or transmission of the signal. So, definitely a cutoff frequency comes into the picture. A cutoff frequency will be there. So, beyond that cutoff frequency, the signal will be transmitted. So, it will be treated as a high pass filter. So, above the cutoff frequency only, the signal will be transmitted. Our transmission line has no such cutoff frequencies. That from 0 frequency onwards, we can transmit with little different attenuation factors. This is one of the most important dissimilarity that what we have. And one more parameter is that here we will have characteristic impedance. That Z0 will comes into the picture here. The characteristic impedance of the transmission line we describe, right? But for our waveguide, there will be no characteristic impedance. Instead, that we will have wave impedance. That for different types of waves, we have different impedances. That's why it is said to be the wave impedance instead of the characteristic impedance of that particular physical medium. So, here wave impedance will comes into the picture. So, that wave impedance also will be described with Z, but we will call that one as wave impedance. And here for the analysis of our transmission line, what we do is we use our circuit theory. Entire transmission line was converted to its equivalent circuit using RLGC. Using those RLGC, we derived and defined different parameters, so that the analysis is purely dependent upon the circuit theory for our transmission line. But for our waveguide, there is no such circuit theory is applicable. Directly the field theory is useful. So, instead of using RLGC, we will use E and H only. That these are the dissimilarities between our transmission lines and waveguides. So, like this, just we can observe different similarities and dissimilarities between waveguides and transmission lines. With this simple introduction, we will go for a special type of waveguide that is called as a rectangular waveguide, and the analysis of rectangular waveguide based on different equations we will go through. We will discuss about rectangular waveguides. As I said, what is the basic shape of that particular waveguide? Rectangle. So, whenever we have a cross-sectional view of that waveguide will looks like this. That this is the front view or a backside view, that what you can imagine. That for your understanding, I am drawing the inner walls as well as outer walls. That this is completely a metallic sheet. That a metallic sheet will be there. 4 metallic sheets will be attached to form a metallic tube like this. So, this is a rectangular waveguide. Now, for this rectangular waveguide and for our convenience, what I do is I will assume that the rectangular waveguide is placed in Z direction. That is, the wave is propagating in Z direction. That is my assumption. You can take any direction for your convenience, no problem. And let us take the broader dimension is along X axis and the narrower dimension is along Y axis. That this is a simple rectangular waveguide that what I am considering. This rectangular waveguide, broader dimension is along X axis, the narrower dimension is along Y axis, and the wave is propagating, or the rectangular waveguide is kept in the direction of Z. And the inner dimensions of a rectangular waveguide along this border is A. That's what I am taking, and this is a universal notation that what you can take. And for the narrower dimension, it will be taken as B. This is also the universal notation. In most of the cases, they will use only A and B. Otherwise, they will use some numerical values for that, right? So, whenever a rectangular waveguide is represented, this rectangular waveguide will be represented as A by B in either centimeter or meter or millimeter. That's purely depend upon the requirement. So, whenever that is A by B is given for our rectangular waveguide, you are supposed to think that this A is meant for broader dimension and this B is meant for narrower dimension. So, this is a simple rectangular waveguide. Now, our main intention is to get the analysis for this rectangular waveguide. So, what are the field equations? What are the field components which exist in this rectangular waveguide? What are the equations for those fields? And what is the cutoff frequency? As I said, this will act as a high pass filter. What is the cutoff frequency for that one? So, what is the phase velocity? What is the group velocity? What is the cutoff wavelength for this one? What are different modes of our wave where it is traveling in rectangular waveguide? Now, we are going to analyze. For that, we are supposed to consider the basic Maxwell's equations, and from that we will get the Helmholtz equations. Already this Helmholtz equation concept is over in our wave propagation. Now what I do is just I will consider those Helmholtz equations. Since this particular medium is filled with the dielectric, no problem, you can consider, right? So what I do is, for this particular region, how the wave propagation will be taking place, that can be explained using our Helmholtz equations. Just recollect what are the Helmholtz equations. The Helmholtz equations are del square Hz is equals to minus omega square mu epsilon Hz. Let us consider this is equation 1. Similarly, del square Ez is equals to minus omega square mu epsilon Ez. Let us take this as equation 2. These two equations are called as the Helmholtz equations, and they are the basic equation for any wave propagation that what we discussed. I am recollecting those equations. Since the wave is traveling in z direction, I consider this as Hz and Ez. Now what I have to do is, I have to manipulate these equations. Just you observe the plot what I am taking. I have to manipulate these two equations and I have to get the solution for these two equations. That when I get solution to get these two equations, I will get pure Hz equation. And if I solve this one, I will get pure Ez equation. So I have two components. One component of electromagnetic wave, that is E in the direction of Z, Ez. Another component in the direction of Z, Hz. Now what about the remaining components, that is the electric field in the direction of X, Y, and the magnetic field in the direction of X and Y, that is Ex, Ey, Hx and Hy. So 4 more components are left for us. So along with those 4 more components, total we have 6 components. That is the electric component in X, Y, Z direction, the magnetic field component in X, Y, Z direction. So if you get those 6 components, that is those 6 equations, then we can manipulate them for our different types of waves. Now my plot is to get Ex, Ey, Hx and Hy using this Ez and Hz. Already we have Ez and Hz equations. We have no solutions temporarily. Later we will get the solution. So temporarily we have Ez and Hz. Using this Ez and Hz, we are supposed to get Ex, Ey, Hx, Hy. So for that, what I do is, I will try to get Ex, Ey, Hx, Hy also. So what are the equations of Ex, Ey and Hx, Hy? Just observe. Now what I am doing is, just I am trying to get Ex, Ey, Hx and Hy in terms of Ez and Hz. For that, consider our Maxwell's equations. That we have a Maxwell's equation, del cross E is equals to minus dou B by dou T. This is the equation that what we have. Minus dou by dou T can be replaced with j omega. So minus j omega B can be written as mu H. This is one of the Maxwell's equations that what we have. Del cross E is equals to minus j omega mu H. Right? Now expand this curl operator. If you are expanding this curl operator, just what you will get? Ax, Ay, Az, dou by dou x, dou by dou y, dou by dou z. Instead of dou by dou z, you can write minus gamma. So this question is already over in our wave propagation. And instead of E, you can write Ex, Ey, Ez. This is the left hand side term that what we have, that I expanded this curl, which is equals to minus j omega mu Hx, Ax plus Hy, Ay plus Hz, Az. So using a simple Maxwell's equation, just expand this curl operator, and on the right hand side you will have this term. Now what you do is, after simplifying this one, make Ax terms equal, Ay terms equal and Az terms equal. Some set of equations you will get, keep them aside. Similarly, we have one more equation. This is one of the equations. The second equation, a similar type of equation is there. That is del cross H is equals to J plus dou D by dou T. That is Ampere's law. So del cross H is equals to J plus dou D by dou T we have. And the medium what we are considering between the walls is a pure dielectric medium, that what I am assuming. For the pure dielectric medium, what you will have is a zero conductivity. Therefore, J is equals to 0. Dou by dou T is simply J omega. J omega and D can be written as epsilon E. So this is the equation that what we are supposed to consider, del cross H is equals to J omega epsilon E. Now expand this one also. If you are expanding this, Ax, Ay, Az, dou by dou x, dou by dou y, and instead of dou by dou z, directly I will write minus gamma. Here it is Hx, Hy, Hz, which is equals to J omega epsilon and instead of E you can write Ex Ax plus Ey Ay plus Ez Az. Now once again, so what you are supposed to do is consider or simplify this one, consider the right hand and left hand side terms which are meant for Ax, Ay and Az, make them equal. You will get one more set of equations. Here you will get one set of equations, here we will get one more set of equations. What you are supposed to do is just club them. If you are making them little mathematical manipulation, if you are making little mathematical manipulation, then all those equations will be simplified. Here all such derivations are not required here. What you are supposed to do is just you are supposed to remember the method what I am following and remember the final equations. The remembering of final equations is very important, because in the problems what they do is they will give you the components Ex, Ey, Hx, Hy, Ez and Hz. So what you are supposed to do is you are supposed to remember what is the form of that one, right? That's why just ignore all the derivations that what we have. Now by clubbing these two set of equations for this set and this set of equations, you will get equations for Ex, Ey, Hx, Hy in terms of Ez and Hz. So what I do is directly I will give you those four equations Ex, Ey, Hx and Hy in terms of Ez and Hz. So as I said, after clubbing those two set of equations, we will get the equations for Ex, Ey, Hx, Hy like this. That Ex is equals to, just what I do is just I will directly write down the equation, you try to remember that one, minus gamma by h square dou E z by dou x, this is the first term, minus j omega mu by h square and dou hz by dou y. This is the equation that what we have for our Ex. That clearly remember, you are supposed to remember this equation. If you remember this equation, the manipulation of this equation is very easy for further applications, right? The minus gamma by h square term is common for all, that whatever it may be the component you are considering Ex, Ey, Hx, Hy, this minus gamma by h square is common for all. Similarly, j omega mu by h square will appears for E term, mu appears for E term and epsilon appears for H term, and this negative sign will vary according to the equation, right? Just if you little bit practice them, remembering this one is very easy. Similarly, Ey we will have as minus gamma by h square dou E z by dou y plus j omega mu by h square dou hz by dou x. So this is the equation for our Ey, minus gamma by h square dou E z by dou y plus j omega mu by h square dou hz by dou x. And as I said, this minus gamma by h square is common for all, and instead of mu you will get epsilon for h, right? So now I will write down Hx equation also. Hx is equals to minus gamma by h square. Here for h, remember that for E initially we are getting E, and for h initially we will get h. It is dou hz by dou x plus j omega, instead of mu write down epsilon by h square, it is hz by dx. So what you will get is dou Ez by dou y. That is the equation that what we will get for Hx. And similarly the final equation can be written as Hy is equals to minus gamma by h square is common. Here also it is dou hz. Here we got dou hz by dou x. So here we will get dou hz by dou y. Dou hz by dou y. Here we got plus. So here what we will get is minus. Minus j omega epsilon by h square. Here it is dou Ez by dou x. So here clearly these are the four equations that what we have. Once again recollect them. If there is any interpretation wrong or the little bit error, just you correct it. Okay, minus gamma by h square dou Ez by dou x minus j omega mu by h square dou hz by dou y, minus gamma by h square dou Ez by dou y plus j omega mu by h square dou hz by dou x, minus gamma by h square dou hz by dou x plus j omega epsilon by h square dou Ez by dou y, minus gamma by h square dou hz by dou y minus j omega epsilon, it's epsilon by h square dou Ez by dou x. These four equations are very important equations you are supposed to remember for the entire analysis of our rectangular waveguides. Just you remember these four equations. These four equations will give you remaining all field components. here what you are supposed to do is, you are supposed to manipulate these equations by substituting Ez and Hz for different types of waves. So here what we require is a solution for Ez and Hz. Earlier we have equations for Ez and Hz, they are the Helmholtz equations. Now what we have to do is, we have to get the solution for Ez and Hz. So what I do is, now I will try to get the solution for Ez and Hz. After getting the solution for Ez and Hz, substitute here. That is the plot, that is the scenario that what we are following. Now clearly once again recollect those Helmholtz equations and try to get the solution for them. But while getting the solution for our Ez and Hz, we are supposed to apply the boundary conditions. As our rectangular waveguide is a bounded medium, definitely some boundary will be there. By applying the boundary conditions, those equations will be simplified. So what I do is, once again I will go to back and I will take those Ez and Hz equations, and I will give you how to, I will give you the step by step procedure. I am not going to derive those entire things, just I will give you the step by step procedure how to get the solution. Okay, later directly I will give you the equation of Ez, directly I will give you the equation of Hz. Now as an example, I will give you how to get the solution for Ez only, later you can go with Hz also, no problem. So the similar equations will be there, so similar steps will be there, and the final equation is also similar except a few terms. So what I do is, I will give you the solution for Ez, that is also in brief, right. Let us consider the Helmholtz equation which is meant for our Ez, that is del square Ez is equals to minus omega square mu epsilon Ez. This is the equation that what we have at the Helmholtz equation. Now you have to expand this equation and simplify and get the solution for this one. For that, expand this del square is dou square by dou x square Ez plus dou square by dou y square Ez plus dou square by dou z square Ez, which is equals to minus omega square mu epsilon Ez. This is the term that what we have, right. Now what is dou square by dou z square? Let's once again go to our wave propagation. Dou square by dou z square can be replaced with gamma square. So this term can be replaced with gamma square, and what I am doing is, I am bringing this right hand side term to the left hand side, then it will becomes plus omega square mu epsilon, and that will be added to this gamma square, right. So the modified equation will be now dou square by dou x square Ez plus dou square by dou y square Ez plus gamma square plus omega square mu epsilon Ez is equals to 0. Now clearly this is a second order differential equation with two variables. What are the variables we have? One variable is x, another variable is y. So to get the solution for this one, what we are supposed to do is, we are supposed to assume that this Ez is a function of both x and y. For that, what I am doing is, I am assuming that Ez is equals to a pure function of x and y. That's x is a pure function of x and y is a pure function of y. Substitute this one. After substituting and simplifying, we will get individual solutions for this x and y. That the x will be like this. X is equals to, if you are getting the individual solution for this x and y, x is equals to some solution you will get in terms of sine and cos. Similarly, y also you will get in terms of sine and cos. So what I do is, directly I will give you the solutions for both x and y. Now what we get is, we get the solutions for x and y. So what is the solution for x? So directly I am giving the equation, don't go for the derivation. X is equals to c1 cos bx plus c2 sin bx. So this is the equation for x. And similarly the equation for y, y is equals to c3 cos ay plus c4 sin ay. So while getting these solutions, we introduced two constants. What they are? A and b. So they are not constants actually, they are the function of both x and y. And we will get one relation between this a, b and h also. So what is the relation we will get between this a, b and h? H square is equals to a square plus b square. This is the relation that what we get in the intermediate step that what we have. Now using this x and y, Ez can be written as Ez is equals to x into y. So while solving this x into y, we are supposed to get this c1, c2, c3, c4, and A, B. Total 6 constants are there. These 6 constants must be obtained using our boundary conditions. That if you are multiplying this x into y, you have C1, C2, C3, C4, not only them, A and B as a function of x and y. So how to get them? So to get them, as I said once again, it's only boundary conditions are useful. Now what are the boundary conditions? To obtain the boundary conditions, once again, recollect our rectangular waveguide. How the rectangular waveguide was placed? So the rectangular waveguide was placed on a plane in such a way that the broader dimension is along x, the narrower dimension is along y, and the wave is propagating in z direction. This is the location of the placing of our rectangular waveguide. The inner dimensions are only sufficient. So the broader dimension is A and the narrower dimension is B. Now the boundary, just you remember the boundary conditions, don't go for applying them and simplifying it. Just you remember the boundary conditions I will give. Here clearly observe how many boundaries are there. There are 4 boundaries. That bottom wall is one boundary for the wave, left side wall is another boundary for the wave, top wall is third boundary, and this right side wall is fourth boundary. So total 4 boundaries are there. Using those 4 boundary conditions, the conditions at that particular boundary, we can solve this C1, C2, C3, C4, A and B. I will give you what are the boundary conditions. The first one, bottom wall. For the bottom wall, observe. So what is electric field? What is the component x and what is component y? What is variable x? What is variable y? And how to apply them? Just the component of electric field is 0 at the metallic boundary. As I said, this is made up of a metal sheet. The tangential component of the electric field is always 0 for any conductor, right? Since it is a metallic sheet and conducting medium, the tangential component is 0. What is the tangential component? We have Ez. That Ez is tangential to this wall. Let us imagine this is the wall that what we have and this is our Ez. As we are saying that the electric field is traveling in z direction, Ez is tangential to this particular wall, right? So here for the bottom wall, clearly you can say that Ez is equals to 0. The tangential component of the electric field is 0. And what is the variable x? The x is varying from 0 to A. That along x direction, the wall is extended from 0 to A. So x can be taken from 0 to A. And what about the value of y at this particular location? Y is equals to 0. So these are called as the boundary conditions for bottom wall. Apply them and simplify the equation. You will not get completely simplified equation, you will get a partial equation. Next, take this second wall, left wall I am considering. For the left wall, once again, what is the electric field component? The electric field component is z direction, that is also tangential to the wall. Therefore, you can consider that one as 0. The tangential component for any conductor is 0. Ez is equals to 0. And yet this wall, what is the value of x? X is equals to 0. For the left side wall, x is equals to 0. And for y, it is extended from 0 to B. This is the boundary condition for left side wall. Apply them, simplify it, keep it aside. And top wall, for the top wall, what is Ez again? Ez is equals to 0. The electric field component for this one also 0, since it is tangential component. And what is the value of x here? X is extended from 0 to A. That for the top wall also it is extended from 0 to A. And what is the value of y? Y is equals to B. That's what we have, exactly y is equals to B applicable for top wall. Similarly, right side wall. The right side wall will have conditions like this. For the right side wall, what is the tangential component of our electric field? Ez. Ez is equals to 0. And for the right side wall, what is the value of x? X is equals to simply A. And y is extended from 0 to B. Now we have 4 boundary conditions. These 4 boundary conditions will be useful for simplifying these equations. That is Ez. The Ez equation will be simplified using these 4 boundary conditions. Now after applying and simplifying those 4 boundary conditions, we will get a fruitful equation for electric field component in the direction of z. Directly I will give you the equation and I will tell you how to remember that one. Just to remember that equation, That's enough. Don't go for the derivation. It's not possible to do all these derivations in your examination. So just you remember that equation. The final form is very important. I will give you that equation. So directly I will give you the equation for Ez. Try to remember it. That's enough. So after getting all those, or after substituting all those things, you will get the equation of Ez will be like this. This is C is some constant, sin m pi by a x sin n pi by b y e power j omega t minus gamma z. So this is the final equation for Ez. There is no solution after this one. This is the final equation, right? Here clearly examine this equation. So what are different components we have? C is some constant, a sinusoidal signal which is purely dependent upon our broader dimension m pi by a. This is dependent upon the broader dimension. Similarly, a sinusoidal signal which is dependent upon the narrower dimension b. And this e power j omega t, which describes that it is a time varying function, and this gamma z will describes it has some propagation constant, and it is traveling in z direction. So just two signs, a sinusoidal signal along a sinusoidal signal along b, and a time varying function along a z direction. This is the simple solution for our Ez, and this is the amplitude of that one, the magnitude of that particular electric field component. Now this m is a constant, this n is a constant. These two will describe how many half wave variations are there along broader dimension m by a. Just you remember like that. M describes half wave variations along the broader dimension. This m describes the number of half wave variations along broader dimension, and n describes number of half wave variations along the narrower dimension. How many half wave variations are there along the broader dimension? How many half wave variations are there along the narrower dimension will be described by these two integers. M and n are integers, right? Clearly remember that point. Similarly, after solving our Hz equation and applying the boundary conditions, for that also some boundary conditions will be there. The boundaries are same, and the electric field component, the tangential electric field component is 0. After applying that one, you will get a similar equation for Hz. That is also will be in the same form, but here instead of sin you will get cos m pi by ax cos n pi by by e power j omega t minus gamma z. So if you remember these two equations, that's enough. These two, along with these two, you have to remember those four equations also. Ex, Ey, Hx, Hy, and the solutions of Ez and Hz. If you go for the analysis of this Hz, it is similar to Ex. This also the number of half wave variations along x direction. N describes the number of half wave variations along y direction. It's a time varying one. It's traveling in z direction, and this is the magnitude of our magnetic field. Clearly, these are the two equations that what we have. Now, what we have to do is we have to substitute Ez and Hz in our field components Ex, Ey, Hx and Hy. Already we have those four solutions, those four equations Ex, Ey, Hx and Hy. Now substitute them, substitute our Ez and Hz in these four. Then you will get pure equations for our Ex, Ey, Hx, Hy. In terms of Ez and Hz, if you substitute Ez and Hz, then that is also will be simplified. Now, don't go for such analysis, because here we have different types of waves. So the wave is not a simple electromagnetic wave. Whenever it is traveling in our waveguide, this will be said to be a specific wave, like transverse electric wave, a transverse magnetic wave, or transverse electromagnetic wave. So these are the three major categories that what we have. Now we will go for analysis of these three individually. So what is transverse electric wave? Initially, the transverse electric wave is nothing but the electric field is transverse to the direction of wave propagation. And blindly remember that transverse means perpendicular. That if the direction of wave propagation is like this, then the electric field is perpendicular to it. Like this, maybe like this, but not like this. That the electric field will not be in the direction of our wave propagation for TE wave. So simply what you can say that the electric field is 0 in the direction of wave propagation. That is transverse electric. In short, it is TE. Transverse magnetic wave, transverse magnetic is similar to that one. The magnetic field is transverse to the direction of wave propagation. Blindly remember, perpendicular. The magnetic field is perpendicular. Let us take this is the direction of wave propagation, then the magnetic field may be like this, like this, like this, but not like this. That the magnetic field along the direction of wave propagation is 0. That's what we have. Now, transverse electromagnetic wave. The transverse electromagnetic wave is nothing but both electric field and magnetic field are perpendicular to the direction of wave propagation. That if this is the direction of wave propagation, the electric field may be like this and the magnetic field is perpendicular to electric field, and that will be like this. Or the magnetic field may be like this and perpendicular to this one, the electric field may be like this. But clearly remember, no electric field and magnetic field will exist in the direction of our wave propagation. This is called as TEM, transverse electromagnetic wave. Now what we have to do is we have to analyze all these field components for such waves. Initially, as an example, I will consider TE wave, and from that you can remember TM wave. So I will give you the complete analysis for TE wave, and remember your TM wave and TEM wave, right? So TE wave is transverse electric wave, that what we are going to discuss now.